person.
All right. What do we have for that chain rule? Derivative of the outside times derivative of the inside. Yeah, that's all it is. Derivative of the outside times derivative of the inside. Okay, so Ryan's going to put the first one up? Yeah. Say what?
Should it be cosine?
The derivative of the sine is cosine.
The derivative of sine is cosine. I don't understand. That's cosine. Yep. Sorry, I didn't see that. Anybody want to put the second one up? There it is. There it is. Do one of you want to put up that second one?
Got it. Do you have to write the work for it?
No, just go ahead and write the answer. We'll just fill in any gaps if questions have. Okay, so we've got a chain rule. The first problem has an outside function of sine, so we take the derivative of that, and an inside function of 3x squared, so we take the derivative of that. So that's what Ryan has done. Took the outside function, cosine, made the cosine, and then he took the derivative of the inside, which is 6x. And just doing the same thing for the bottom function. Okay, she brought down the 2, so she had 2 times 4x cubed plus 7. Okay, and then she multiplied that by the derivative of the inside. So an intermediate step here would be 2 times the inside, right? That's the power rule. This is something squared, so that's 2 times something to the first power, times the derivative of the inside, which is 12x squared. And so she combine the 12 and the 2 to make it 24. Okay? So this, we know that in this chapter we're talking about integration. And I just had you take a derivative. And tell me a little bit about taking a derivative and taking an integral. What sort of process, compare the two processes. They do what? Okay, one finds slope, right? The other finds the area. How about comparing the two processes? Oh, yeah, one's working forwards, one's working backwards, right? Which one works forwards, which one works backwards is debatable, right? But the bottom line is they're reverse processes of one another. Okay, so when we're doing a chain rule here, if you notice, we're taking the chain rule of this single expression, and we end up with 2 expressions. And if we look at these 2 expressions, can you see a function in its derivative in each one of those expressions?
Yeah.
A function and something that's close to its derivative, but we know it's multiplied by 2 here. Okay? So the idea is that as we do the chain rule, we get this pattern of an expression that has a function and a derivative in it. Okay? Well, if integration is just working backwards, and I think this slide number 2 is in the wrong spot, so I'm going to come back to slide 2. If the process of integration or anti-differentiation, really, I guess I really should be saying, is anti-differentiation since we don't have upper and lower bounds, can you see a pattern in this expression that has a function and a derivative of a function? Which is the function? Where's the function and its derivative?
3x squared.
Do we see a derivative of 3x squared in this expression? Yeah, so we can call this kind of a chain function, and this is its derivative. Okay, so in other words, we must have gotten this by doing some sort of chain rule. In fact, you did this on the first page. I could ask you to actually integrate this, and you would get what back? Yeah, right? You would get right back to where we started, because we know that differentiation and integration, those processes reverse each other. Okay? Does that make sense? And then can you see a function and a derivative here? Okay, what's the function? Yeah, when in terms of powers, the function is going to be which power? And the derivative of that function is going to be which power? One littler, right? So we know that if this is the function with the higher power, must be some sort of derivative of that function. Now, what is this derivative? If I just look at this, yeah, isn't the derivative 12x squared? How much of the derivative do I have out here? I have double it, right? Wow, there we go, double it. Okay, so this is 2 times the derivative, really, is what it is. Okay, so we're going to learn to identify those, because if we can look at a product of 2 things and say, hey, wait a minute, I've got a function and its derivative as that product, it makes the integration process a lot simpler. Okay, bless you. So we're going to look at a couple of examples just like this. So really, I just got done saying this, anti-differentiation falls into this pattern of having some sort of function and its derivative. Okay, and so in really calculus-y terms, okay, we have the function and its derivative in that anti-differentiation notation. And what we're going to do is we're going to do something called a U substitution. The only reason why we call it a U substitution is because we use the variable U. Okay, but we're substituting out. So what we do is we say, well, let's call this whole thing U. Okay? And if that whole thing is U, then this must be the derivative of U. And so what happens then, I always chuckle because maybe nobody sees it but me. Does anyone see FU? Yeah. Hello? Calculus books? I don't know. I always chuckle every year when I see that. I'm like, that's kind of funny. Anyway, so the idea is that we can then substitute out something really complicated for something a lot more simple to take the antiderivative of. Okay. And so it works kind of nice in that respect. So let's kind of try this. This is similar. Do you see a function and do you see a derivative?
Yes.
Okay, what are we going to call our function?
7x squared minus 2.
Yep, and we are going to label it U. I agree. So I'm going after that function, and if you notice, really what we're focusing in on is, do we have a set of brackets where we can pull something out of the brackets and just call it U? Okay, if we can, let's do that so that we don't have this complicated thing in the brackets. If I call this U, then what is the derivative? If I took the derivative with respect to x, right, that's my variable that I'm working with here. What's the derivative of 7x squared minus 2? 14x. So the idea is I can have a simplified expression, and then I have to look at this, this expression of the derivative. And we're going to go through a substitution process here to get everything that has an x in it removed. So when we look at this, if I broke this, if I kind of separated this out, we would have 7x squared minus 2. We know we have to substitute that out. So we're going to substitute that out. And we also have a 28x dx. That comes from these 2 terms. And all I did was I rearranged them. And they're all multiplied together, so rearranging isn't a problem. Do you see a 28x dx in this expression? I rearrange this to say du equals? Okay, how do I rearrange this to say du equals?
Multiply both sides by dx.
Yeah, and really, I know we're using the term multiply both sides by dx, and that's okay. Really, what we're doing is we're relocating this differential expression to the other side. So we end up having a 14x dx. Well, what do we need? Do we need a 14x dx or do we need something else? We need a 28. So how many du's do we need?
2.
2 of them. So 2 du's equals 28 x dx. Okay? So now what I have is I have a way to substitute out that whole expression. And instead of 28x dx, I'm going to call it what?
2 du.
I'm going to call it 2 times du. And instead of 7x minus 2, I'm going to call that what? U. So if you notice, the entire x variable is gone. And we're left with integrating what? U to the what power? Cubed, yeah, U cubed. How many can integrate U cubed? Not bad, right? A lot easier than what we started with. Does that make sense? Now we do have a 2 out front. What can we do to that 2? That constant 2. What can we do? Put it on the outside, exactly. So it's really 2 times U cubed du. So any constant, just like with differentiating, right? Any constant that we have up front, we can just pull out of the calculus part and multiply it at the end. So what is the integral of U cubed du? What's the antiderivative there? Bump up the power. Yep, bump up the power to a 4, divide by that new power. Don't think about it too much. Just bump up that power and put that new power in the denominator. Okay, and of course I also need a plus what?
Du.
No.
U.
Oh, U.
No.
C.
Yeah. Right? The du and the integral sign, the antiderivative sign and the du go away after we've done the integration process. Those are part of the notation for please find my antiderivative. Right? Now, we started out with a problem in terms of what variable? We need to end up with an expression in terms of that variable. So what do we have to do to get the u gone?
Let's 7x minus 2.
Put 7x minus 2 back in. And 2 over 4 is 2 really in where? Denominator. So integrating, I can't even remember the original problem now. Integrating 28x, I think I forgot a square there. Integrating 28x times 7x squared minus 2 cubed gets us that. Okay. So the idea is, was it a lot of substitution? Was it a lot of algebra? But the bottom line is that algebra and that substitution made integrating a really quick process. Because after we did all of that substitution, we were just left with integrating u to the 3rd power. Okay? We can do this with slightly more complicated expressions, like tangent of x dx. Does anybody know what the integral of tangent x dx is?
Secant squared.
What's the derivative of tangent of x? I know. So Tyler said, oh, it's secant squared. No, that's the derivative. Right. Okay, yeah, so it's something that doesn't even really look that close to tangent x. So what we're going to do is we're going to rewrite this as sine of x over cosine of x. Yep. We're going to rewrite it using a trig identity. And now, what do you know, I mean, about substituting u in for one of these values and then taking the derivative of that? What's going to happen? First of all, what do you want to call u? Go for the complicated portion of this expression. Sine or cosine? Which one? They're both not that complicated, but which one's in a location that seems to be problematic? Cosine, exactly. So go after calling that u. Okay, we're looking at things. When we look at an expression, we're looking for things like, what makes this more complicated than I would really like it to be? Well, the presence of a denominator, definitely. Things in brackets make things more complicated than you really want them to be. Things underneath radicals, right, square root signs and stuff like that, make things more complicated than you really want to deal with. So go after getting rid of that stuff. So if my u is going to be cosine x, then if I know I need to take the derivative of this, what's the derivative of cosine? So what is the derivative negative sine of x? Okay. So if I rewrite this, in other words, if I take this expression and put the dx over with the x variable, I get something that looks like what? Yeah, du equals negative sine x dx, right? That's where we kind of just say, oh, just multiply by dx. It's kind of what's happening. We can say that on a superficial level. We're really separating the differentials. We're saying, let's stick all our x stuff on one side and stick all our u stuff on the other side. Okay? Do we have a negative sine x dx here? We have something really close, don't we? We have a sine x dx. So in other words, I can look at this as sine of x dx over cosine of x. That would be another equivalent way of writing it. Is this a du or something really close to a du? Really close. It's a what du? Yeah, it's a negative du. So I need a positive sine x dx, and I have a negative over here, don't I? So I can rewrite this saying, well, that's the same as saying a negative du equals a sine x dx, or a positive. So I'm going to take this and do a substitution for this. And then what's my substitution for the bottom? Just the u, exactly. Okay, so if you notice, we have to substitute everything out that has that x variable. So looking at that then, I end up with a negative du on the top and a u on the bottom. I'm trying to color code here. So I'm left with integrating, or taking the antiderivative of that. Okay. Does anybody know what the antiderivative of that is?
U to the 0.
Okay. So if we rewrite it, I'm going to bring the negative sign out front. That's like a -1, right? Mathematically, it's the same thing. And I know what Amanda just was talking about, a negative power. I'm gonna get there. Du over u is the same thing as saying 1 over u times du, right? That's just manipulating the expression, right? And then you can always just write the fraction and then the du. And then Amanda, I think you were saying that's u to the -1.
Yeah.
Right? What's the antiderivative?
U to the 0.
Wait a minute. U to the 0 divided by 0 was a problem, right? What is the antiderivative of 1 over u? Natural log. Exactly. So we have minus the natural log of the absolute value of u plus c. We can't bump this up to a 0 power and divide by 0, right? It's not defined. Scroll. Wait,
Like so I can see the stuff.
like this stuff?
Uh-huh.
There you go. Okay. Yeah, exactly. Wow, that doesn't look anything like what we started with. That's okay. You know, we're going to get something in this last step that's kind of messy, but at least the integration was okay. So 1 over u, antiderivative of that is natural log of u. And I already hear a couple of tables saying, well, if I substitute back in cosine of x for my u, I get the natural log of the cosine of x plus c. It's messy. It's okay. At least the integration wasn't that bad. Okay? Doing okay so far? So at least that integration wasn't too bad. Or that anti-differentiation. Oh yeah.
What makes cosine x and u?
Pardon me?
What makes cosine x u less than the u?
Only because that's what I decided to do. I looked at this and I said, what makes this complicated is that I have a fraction. What I really don't like about fractions are denominators. So I'm going to get rid of that and make it simpler. So I'm going to call that u. Okay? And then the only reason I did that is I said, well, I know whatever I call u, I'm going to have to differentiate it, right? And if I differentiate a cosine, I get a sine. Which means if I call this u and take the derivative, I actually get to get rid of that too. That's a bonus. Does that make sense? Okay, and that's kind of how we approach these problems is let's get rid of something and then the bonus is that when we take the derivative, we also get to get rid of something else. Okay? Any other questions? Okay. The last thing before we kind of start to practice this is we need to be able to handle definite integrals as well. So we need to be able to handle the upper and the lower bound. Okay? So you remember when we have a definite integral, we have to find the antiderivative, right? Which is what we're doing. That's that whole process. And then we have to evaluate the antiderivative at the upper and the lower bound. Okay, and so remember in chapter 5 we would write that a lot. And we'd say, oh, what's the antiderivative of this function? And we could just kind of see it a lot of times. And then we just do to evaluate it at the upper and the lower bound. Now we can't see the antiderivative as easily. So now we're going to have to go through the substitution process, the u sub process, in order to get the antiderivative. Okay. Now here's another situation, and we're gonna be working with these next two assignments for a couple of days. Bless you. And so, you know, like for the rest of this week and into the beginning of next week. So we're going to try to get comfortable with these things. So there's a you know, these definite patterns, like factoring out stuff or substituting out stuff in brackets or substituting out stuff in denominators. The other kind of pattern is sometimes you'll have a radical in the expression. And radicals are messy. So wouldn't it be nice if we could substitute out everything in the radical? So looking at this radical, can you see that we have a function and its derivative? Okay, so what's going to be our u here? Okay, well, not the square root. We're just going to take the stuff in the square root. So we're going to call u x cubed plus 1. Which means du dx is what? Equals 3x squared. Separating our differentials, we get du equals what? 3x squared dx. Okay. Do we have a 3x squared dx here? Yes, we do. Exactly. So if I'm just going to rewrite this, and you have to decide on your own if this step is worth it to you. Okay. But I was very kind of methodological when I did the tutorials. I always rewrote it so you saw the u and the du. Okay, so you have to decide. You know, is it worth it for you to rewrite it like this, or can you put the pieces together without rewriting it? So I'm going to go ahead and substitute out everything under the radical here.
Should it be x to the third right there?
Yes, it should be. Good catch. Change that to a 3. There you go.
Oh,
Well, you know, I get good every once in a while. Okay. And so now I've got my du here. So what do I end up having in this portion? And we generally call this the integrand, okay? So what do I have in the integrand? Instead of this, yep, exactly. I end up having the square root of u times du, okay? Now, this is kind of interesting because we've done a couple of examples, and we always get these. We always substitute, get it in terms of u, find the antiderivative, and then put it back in terms of x, right? But this one's a definite integral, which means we have numbers that we're going to use and plug those in to find a value. But this -1 and 1 refer to what variables? X. So to put -1 and 1 here and not have an x here wouldn't be appropriate. So we need to find our lower bound and our upper bound for our u's. How do you think we're going to do that? Carly, what's up?
Where did the first 3x squared go? Like in the original version?
Right here?
Yeah.
I put it here.
But I thought that was d.
It is. So what I did is I took out 3x squared dx, 3x squared dx, and I replaced it with the du. Okay? So this substitution is saying I can remove this and put in this.
But isn't that just the derivative of the inside
Mhm.
of the original function?
It's the chain rule. Right? This is the function, and this is the outside is the square root of u, and the inside is this, and we took the derivative of it. Any other questions? Does that make, are we good? No? Can I answer another question? No. Let me know. Okay. So we've got to find these replacements. So we know that these lower and upper bounds refer to x. So if x equals -1, here's my lower bound. If x equals -1 and I put -1 here, what do I get for u? Yep, exactly. I put a -1 here, I cube it. How much is that? Plus 1
0.
is 0. So my new lower bound is 0. That's my lower bound for my u. What about my upper bound? If my upper bound for my x is 1, and I substituted out my x and put in this instead, then how much is my upper bound for u? 2, exactly. So we call that a change of limits. When we change the variable, if we have a definite integral, we need to change the limits of integration. The nice thing is that we don't need to go back to x now. We've rewritten everything in terms of u. We can evaluate it. We don't need to go back to x. We can forget about it for definite integrals. So that's kind of a nice bonus. So we have to integrate u to the half power du, which is nicer than trying to integrate this from 0 to 2. And we will end up getting the same answer as if we tried to integrate that.
Do we have to put it to the 1/2?
No, can you see what the antiderivative is? Just leaving it like that?
Yeah.
Awesome. Go for it. Yep. I only do that because I like to re-emphasize the whole power. So bumping up my power by 1 gives me u to what power?
Like that.
3 halves, right? I look at this and I say, okay, I got to increase it by 1, so I got to increase it by 2 halves, is what I think. So 2 halves and 1 half is 3 halves. And then we just divide by the 3 halves. Okay? Dividing by 3 halves is the same as what? Multiplying by 2/3, the reciprocal. Okay, so here's the new notation. We have to evaluate that at what 2 bounds?
I have to add c though.
But that's if we don't have an upper and lower bound. Great question. Amanda just said, don't we have to have a plus c? If we had the antiderivative, we'd have to have a plus c. And in fact, we'd have to go back to x then too. But we have a definite integral, which means we're going to evaluate this at the upper bound and subtract the evaluation at the lower bound, right? We're going to basically do our f of 2 minus f of 0, our big F's, okay? Because here's our big F. Okay, so the plus c is gone because we're finding a number. So this is the notation. And I'm actually, this is not the notation, but I'm going to go back to this. Remember this from the last chapter, right? And we just plug in the 2 and plug in the 0 and get our answer. The notation that was getting you ready really for this chapter. The real notation is this. Once we have the antiderivative, when we evaluate it at the upper and lower bounds, we just draw a big vertical line, because that big vertical line tells us we have the antiderivative, and we're going to evaluate it at 2 and 0. So we're going to plug in 2, and then plug in, whoops, got a colon sign there, minus, and then plug in 0. Okay? And so my answer is how much to 3 decimal places? Two to the 3 halves power is definitely a decimal, right? It's a cubed root of, it's this square root of 8. And then we have to multiply by 2/3 and we get what? Can someone crank out that? 1.886? Sounds believable to me. 2/3 of the square root of 8 That seems believable. Okay. How we doing? Okay, we're doing okay. So really, what we're looking at, I should have rearranged these pages actually. There we go. I'll put this back here because I think people are probably not done writing. There we go. So really what we're looking at is we're looking at basically 1, 2, 3, 4, 5 types of U subs I could ask you to do. And those are on your last page in Notability. Can I change that to the last page? Would that be okay? I just didn't want to cut anybody off writing wise. We're talking about, and we had an example of a polynomial where we had, x cubed plus 1 and 3x squared as the derivative. Any type of fraction, like our sine over our cosine, some trig stuff, some exponential and natural log, and some radicals, square roots and cube roots and stuff like that. That's really what the categories fall into for a U sub, is those 5 categories. Okay? So any questions about